Dear all, in this video I will be working on a problem from graph theory, which is about simple graph's chromatic polynomial. So if you're interested in graph theory or computer science, this is just the right video for you. So let's get started. Welcome again. So our problem is trying to find the chromatic polynomial for the graph below. So before we jump onto this problem, I want to briefly explain what a chromatic polynomial is. So we are trying to find unique colors for each vertex. Our colorings will be unique. So when I mean unique, it should be different than the vertex before itself. So if this vertex is adjacent to this vertex, they cannot share the same color pink. So if I were to write a color, I had to do blue. And now this next vertex cannot be blue because it's adjacent to this blue vertex. So we're gonna have to go with another choice, and we're trying to use the minimum number of colors we can to complete this problem. So we can go with pink again. Okay, and now we have a bunch of new points. Okay, and the chromatic polynomial is basically about the idea of how many possible colors can I choose here. So we usually start with a number k. Okay, so our first point will be any k number of colors. Okay, so if you have 10 colors, it could be any one of them. Okay, but about the second point, that's a little blue point, it cannot be pink. Okay, that's the only exception. It could be any other color though. So from the pool of my colors, I would have to eliminate the pink one. So if I were to have 10 colors in my pool, I have only 9 colors. So this is a little bit about kind of similar to probability, the probability of having a different color. So now, likewise, pink one is also, the next pink one is k minus 1, because notice how the blue one is adjacent to the pink one. So the blue one, it cannot be blue is now the requirement because it is connected to a blue vertex. Okay, but the first one had a freedom because it was not connected to anything. It had no source coming in, but we have source coming out of that. Okay, so now we have a triangle here, and the little connection from the one vertex of the triangle to the other vertex of the end of the triangle. So now things change a little bit. This is where it gets a little tricky. Okay, I'm gonna use another color. Let's go with blue again. Okay, well now look at this color. Well, the only one, we can go any way, by the way. We could go up or down, it doesn't really matter, because we have to get the same result. Algorithmically, it will give us the same result for k, because we are doing literally every option is just gonna balance each other out, basically. So now for this blue one, imagine I'm just connected to pink right now. What are my possibilities? So I cannot be pink, but I could be blue. So I'm gonna use blue because I want to use the minimum number of colors. So this will be also k minus 1. But now, please notice, we have a problem. Now, if I want to go to this vertex, I cannot use pink or blue. The reason is simple. The reason I can use pink or blue is basically because both of them are connected to this vertex. Look, both pink and blue are adjacent to this vertex, adjacent to this vertex. So what can I do here? Well, I have to use another color. Okay, and that color is going to be green. Well, it could be anything, basically. But now my number of colors are limited here. My options are getting smaller. So imagine your color pool. Okay, I used pink and blue. So now among, let's say, the 10 options again, I think it's easier to work with arbitrary numbers. I don't have 2 options anymore, so I will have 8. So I will have k minus 2. Very, very simple. If abstract numbers like k seems confusing, I would suggest imagine a color group. Okay, I mean we are trying to find the minimum number of colors basically. So we will not have a bunch of different colors. We're gonna have a few. So if you want to have, let's say, I don't know, blue, purple, green, red, yellow, or whatever. You can have 5 colors. Maybe even 5 colors would be efficient for most problems like this, for simple graphs. So, thinking with numbers is always going to make it easier to understand this abstract term here. Okay, that's good. So now we are at this vertex, and this vertex is, notice how it's connected to blue, green, and pink. This one is also a connection on the top, the curve. So we're gonna have to use not pink, not green, and not blue. So we have 3 options being limited from us. So what we can do is, I don't know. I mean, I didn't use purple, so I'm just gonna use purple. I mean, so that's one option, and my value should be what? Well, think about it. We use blue, green, and pink. All 3 of them are not usable. We're unable to use them. So we're gonna have k minus 3. It's just really simple logic. Okay, and now we can go back to this little path down below. And now we are connected to blue. Well, this blue vertex connects to 1, so the only requirement for this vertex is just going to be not blue, okay? Not blue, so I can do pretty much anything other than blue. So, let's do green, right? Okay, and this is also going to be k minus 1 because blue is just the only one that is not allowed to use for that vertex. Now, for this one, the one down below, it is both connected to blue and green, so it should be not blue and not green. So I just decided to use pink here. I'm just going to be using pink. And now my options are also limited a little bit. We are going to have k minus 2 colors. Likewise, I have another triangle. Okay, anytime you have a connected triangle, you cannot have any one of all of them have to be unique colors basically, because each edge, each vertex is connected to each vertex in a triangle. Every vertex is connected to each other, which means when you are dealing with a chromatic polynomial, we're gonna have like a factorial a little bit, not an entire factorial, but k times k minus 1 times k minus 2 kind of logic. Okay, so for the blue one, did we do the blue one? Not sure. For the blue one, we're gonna also have limited options. We're gonna have not green or not pink, so we chose blue, so that's gonna be k minus 2. The one down below can be purple. It doesn't really matter. What matters is what you have there. So also k minus 2 because it cannot be either blue or pink. And we're going up. This is only connected to blue, so the only requirement is for it to be not blue. So I'm just gonna say k minus 1. And these two, obviously not blue, but we could say green. These two will be different coloring, so our color for that one is gonna be k minus. We use pink, so let's go to blue first. So we're gonna have k minus 1, and for the green one, I'm gonna have k minus 2. Okay, that's it. That's all. The reason we have k minus 2 is because the green one is connected to both blue and pink, so that's why it has to be not blue or not pink among the pool of colors. So it's just k minus 2. So now, here it comes, building the chromatic polynomial. So you're going to take every single little polynomial you have, every single first degree, and combine them. So how many how many k's do I have? Obviously, I have to have only one k. Okay? Because that's where it starts from. If we are talking about a connected graph, every edge vertex is connected to one another. Well, the first one should not be coming from any other vertex. it should be the starting point, okay? Which is why we will have only one k. Okay. We're gonna eliminate k here, and now how many k minus 1s do we have? Let's combine like terms so we can have a really nice looking polynomial. So that's gonna be 5, 6, I think 6 ones. K minus 1 to the 6th power. Okay. And now let's think about k minus 2s. So we have one k minus 2 here, one here, here, and here. So I'm gonna have 1, 2, 3, 4, 5 k minus 2s. And the only thing left will be k minus 3. And this, ladies and gentlemen, will be our chromatic polynomial for this specific graph.